Dimming done right. How to properly dim LEDs. There's a lot that can go wrong. Artificial light is a very important factor for human society. We started with fire, then we invented the incandescent light bulb, and today we are using luminescent light sources. And the light sources are getting more and more intelligent. With each of these steps, the safety of using the light and the comfort of using it has increased. Properly dimming LEDs can be quite a challenge. LEDs have a very wide dimming range. They can be dimmed down to the very edge of perception. So customers are expecting a lot more features of an LED light source than of an incandescent light source, like color mixing, human-centric lighting, and more. But it's always a challenge to find the right spot between cost, efficiency, and possible lighting artifacts due to dimming. The first question about dimming is, how do we get the dimming information to the lamp? There are a couple standard methods, like phase modulation of the mains power, like it is used with the incandescent light sources, analog control or digital control. Phase modulation of the mains power is backwards compatible, a well-known technology, and there are lots of existing installations. But since it works by cutting off the sine wave of the mains power, it has rather bad efficiency, a bad power factor, which means a lot of noise on your mains. It does not have very much control, there's no back channel, and the cabling defines a function, which means if you want to reassign a lamp to a different dimmer, you have to pull in a new cable. Analog control is also a well-known technology. A voltage level controls the brightness of the lamps. This is easy to implement, but it also gives you only a low control level, has a high risk of interference, like if you're unlucky, a cell phone can make your light flicker. It has no back channel, and the cabling again defines a function. If you want to change anything about your installation, you have to pull in new cables. So this is an old technology, don't use it. Digital control gives you a lot more options. Since power supply and signaling are separate, the signaling can be wireless. It gives you full control over your light, you have a high reliability, and you have flexible functions, so reassigning a lamp to a dimmer is a software feature here. You don't have to pull in new cables. Of course, that comes with a more complex installation, and there are many incompatible systems on the market, but this is a way to go, it's worth it. So we now know that dimming is best done digital. But how do we dim the LED physically? Varying the supply voltage to the LED is not really an option. The difference between the voltage where the LED produces no light and the point where the LED overheats is very small, so varying the voltage is not such a good idea. The possible options are to change the current through the LED or to use a pulse width modulation. Changing the current for dimming has the advantage of not interrupting the light stream and not producing EMC problems by dimming. But LEDs can change their color depending on the current, and there is a non-linear relation between the current and the light output as LEDs get less efficient at higher currents. And the driver topology is usually a bit more complex and not as efficient as other options. Pulse width modulation is basically flicker as a dimming method. The LED always gets the same current, but it's periodically switched off. And the ratio between on and off times define the perceived brightness of the LED. This is highly efficient, simple to implement. The LED always gets the same current, so it does not shift the color, and there's a linear relation between the dimming value and the light output. High resolutions are possible with this method, but you can have EMC problems with higher frequencies. Not all regulators are capable of doing this, and you can have artifacts in the light that might disturb. Here's an example of a too slow pulse width modulation. It runs at about 70 Hz, and it generates significant artifacts with a camera, and it's also not really pleasant to look at with a naked eye. Most of the problems go away with a higher frequency of the pulse width modulation. Frequencies above 500 Hz are usually not directly perceptible, but other problems may arise, like electromagnetic compatibility, and not all LED drivers can do very high frequencies. In many of our designs we use 730 Hz as a good compromise. This example uses 730 Hz for the pulse width modulation. You can see there are still some artifacts with this specific camera, but with the naked eye there are no effects visible anymore. The smartest pulse width modulation you can have is Spectrum PWM. It borrows a technology from modern radio systems and spreads the signal over a wide frequency range that appears like noise. This makes a lot of problems go away. This example uses a Spectrum PWM, and as you can see anything. At least you can't see any problems, you can't see any artifacts, just dimmed light. A practical example of a driver using Spectrum PWM is our LED Warrior 04. It uses frequencies between 182 Hz and 187 kHz, so that's faster than many DC-DC drivers use for switching. So how do we do the dimming now? The answer is, that depends on your application. If you have something that's cost sensitive, you might aim for one of the lower end options, and if you need the high quality light, then you might go for Spectrum PWM or even for current controlled dimming. Thank you for watching. Please don't forget to like and subscribe and come back for more.